Okay, so in my last video, which was Unit 1, Section 3, Part 1, I thought I was going to be able to get through it. This is where we stopped. We were talking about chemistry, temperatures in chemistry, using Celsius and later on Kelvin, but it was just such a long set of notes, I wanted to split it. So this is where we're starting. Again, it's the same set of notes. I'm splitting it in half, and we're going to move on into some more of those measurements and things that we're going to be using in chemistry. So what we're going to talk about in this set is we're going to start with significant figures or digits. Sometimes we refer to them as Sig Figs. It's just easier to say than significant figures every single time. Anyway, trying to determine how we figure this out. So when you're reading an instrument, such as a graduated cylinder or a thermometer in chemistry, you really have to produce an estimated digit, okay, because you're kind of eyeballing it. Measurements include precise digits plus a last digit that is really estimated, especially when you're getting down into those smaller decimal places. But significant digits are all known values, and they are used in rounding and reporting numbers in science. Okay, let me move myself out of the way. Come on, there we go. All right, so there's rules that you have to know. Okay, and I've given you some examples under each rule, and the red numbers show if I'm pointing out like certain things based on the rule, they would be considered significant. So any number one, any non-zero digit, so anything 1 through 9, that's always significant. You would always count that as a sig fig. All right, zeros is where it gets kind of confusing because there are a few rules for those. If there are zeros sandwiched in between two significant digits, like the ones I have in red there. Now, of course, the 1 and the 2 would be considered significant, but I wanted to make sure that the zeros were highlighted. Those zeros would be significant, okay, because they are in between two non-zero digits. So technically, for 1002, if I asked you how many significant digits or figures were in 1002, you would tell me 4, because the 1 and the 2 count, and then those two zeros that fall in between the 1 and the 2 also count for that. All right, so if you're looking at, let's say, a decimal, looking at number 3, a 0 to the right of a decimal and at the end, so, the one that's directly after the 1 there, that would be considered significant. Notice how I did not highlight these right here. Those are considered just placeholders. Let me show you. If you look at number 4, zeros just to the right of the decimal, whose only function is to really hold these places, until you get to some other significant digits right here. Those zeros would not be counted. Okay, would not be counted. So in that one, you only have 2 significant digits, the 2 and the 5. All right, and the 5th rule, trailing zeros in numbers are only significant if the number contains a decimal. So we have 100 there, and then we also have 100 again, but 100, the second one has 100.0. All right, we wouldn't be writing this 0.0 unless it was significant. If there was no other significant figures like a 1 through a 9 over here somewhere. So there would be no point in writing that unless it was a significant one. Okay, so in this case, we did not put a decimal. These zeros don't count as significant. It would only be this one here, but since we put the decimal point and a 0 following, all of them are considered significant. Okay, now I did a video where I'm walking you through some significant figure examples, so you can watch that other recorded video to see more examples if this confuses you. But really, you just kind of have to learn those rules. All right, where and how do you round numbers? You round your answer. You never round during a calculation. I'm going to walk you through some examples on how to do that in a video as well. So let's say you're given a problem to answer, 3004 plus 0.0045, and you don't round the numbers that are in the actual problem but when you get to your answer, and that's when you round. But we've got to talk about how to do that. And you don't double round. So, for example, 3.48 is 3 and not 4. Okay, so 3.48. You could say 3.5, but again, it depends on the number of significant digits you have to have in your answer. All right, multiplying and dividing, you round to the least number of significant figures that you were given. So if you're multiplying or dividing, and again, I'm going to go through some examples with you in a different lecture, but you are going to have to look at the number of Sig Figs that are in the numbers that are in your problem. Figure out which one has the least number of Sig Figs, and then your answer has got to have the least number of Sig Figs. When adding and subtracting, that's a little bit different. You have to look at the decimal places. You know, how many spots are after that decimal point, and whichever number in your problem has got the least number of decimal places, that's what you're going to put your answer in. Again, I know it's kind of confusing just for me talking about it, but there is a video that shows you how to do this. So, all right, exceptions to Sig Fig rules. The numbers that have infinity significant figures, like counting numbers, if you count out something, known constants such as pi, you know, that can go on forever. Numerals like a dozen, a pair, and we'll talk about moles later, and atomic masses. So those are things that pretty much have an infinity number of Sig Figs. All right, let's look at an example. And again, I made another video that has multiples, but let's just look at one for now. How many significant figures are in 0.0037? And remember your rules. The ones that apply to this one are all numbers, all 1 through 9 digits are significant. So we know the 3 and the 7 are going to be significant. They fall between the 1 and the 9. Zeros just to the right of the decimal, whose only function are placeholders, okay, are not significant. So like for this one, 0.005, these will not be considered. So looking at this one, this 0 and 0 here are really just kind of placeholders until you get to the 3, 7. And since there's no significant on this side, we don't count these zeros. So your answer here, the only 2 significant figures in that are the 3 and the 7. Again, if you need extra help, watch my other video that just takes you through 5, 6 examples of how to figure significant figures. Okay, moving on to scientific notation. This is given, it's a given number written as the product of 2 numbers containing a coefficient, which you see down here, and and 10 raised to a certain power. In chemistry, you will work with very large numbers and very small numbers. So we do have to write a lot of them in scientific notation. Otherwise, we'll be writing like 12,000 zeros across the page. So don't want to have to do that. So how do I write numbers in scientific notation? So again, it's based on powers of 10. And your rules are the coefficient. So when we say coefficient, we're talking about this number right here and this number right here. Has to be between 1 to 9.9. Okay, so you move your decimal point. In this case, we need to move it down here so that we end up with a number that's between 1 and 9.9. So you count how many places you move that decimal point. 1, 2, 3, 4. Okay, so the decimal point goes there now, so you end up with 6.29. And you multiply it by 10 to a power. Or what do you put here as your power? It depends on how many places you move that decimal point. Well, we moved it 4 places. Now, why do we have a negative? Well, that's because we started out with a number that was a decimal, and it was very, very tiny. So we end up with the negative number here. Now, on the other hand, we have a large number here. It's not a decimal, 2030. Where is your decimal point here? It's at the end, behind the 0. We have to get to a number that's 1 to 9.99. So how do we do that? We move the decimal point 1, 2, 3 times. So we end up, and that's where the decimal point will go. So we get your 2.03 times 10 to the third, and you see here the exponent is positive because we were moving in the other direction. And this is a bigger non-decimal number. So again, I've got samples on how to do this in another video lecture if you need that practice. Okay, multiplying and dividing scientific notation can get, you might have to go back and watch a little video on how to do that, but multiplying and dividing, what you do is you do that to the coefficient first. If you're multiplying, first coefficient by the second, which it doesn't matter if you're multiplying, but dividing, divide the first coefficient by the second one. When you multiply, you're going to add your exponents. When you divide, you subtract your exponents. And you have to express your answer in proper scientific notation. So again, that the coefficient is between 1 and 9.99. When you add and subtract, you have to make sure that the exponents are the same. So you will have to adjust your coefficients and so you can adjust your exponents. So when you add the coefficients, and then you follow it with whatever your power of 10 is, which at this point should be the same for both in your problem. And subtraction, you subtract. And again, you have to express your answer in so that the coefficient is between 1 and 9.99. Okay, I got some sample questions or problems on that too. So this one is just showing you scientific notation, number between, and this is your coefficient, 1 and 10. Actually, it should be 1 and 9.9. And an integer of a power of 10. So for example, 5.2 times 10 to the third, 8 points. This is just showing you some scientific notation examples. All right, if you're converting to scientific notation, move the decimal point until there is only one digit to the left. If you're moving the decimal point to the left, the exponent goes up. If you're moving the decimal point to the right, the exponent goes down. So, for example, here we have 156,000. Again, you would move that decimal point 1, 2, 3, 4, 5 places, and we're moving it to the left. So 1.56 times 10 to the fifth, again, it's positive. And then for this one, we're moving it to the right. How many times? 1, 2, 3, 4, 5, 6. 5.3 times 10, and we said the exponent goes down. This is where we're doing the decimal, a very small number at first, so that would be a negative 6. All right, addition and subtraction examples. So when you add and subtract in scientific notation, you have got to make sure that these exponents are the same. See how we start with 10 to the third here and 10 to the second here. We can't do it until we get them to the same. So we left this one, and the way we fixed it was we just moved this decimal over one more, and then we changed our 2 here to a 3 because we moved it one extra space over. So now we have both 10 to the third, and really all you do is 6.02 plus 0.314. You get your coefficient answer multiplied by 10 times power 3. For multiplication, these are a little bit easier. You just multiply your coefficients. So in this case, it's 2 times 10 to the fourth, 3 times 10 to the third. You're just going to multiply the 2 times 3, end up with 6. The base of 10, you don't do anything with that. Okay, you don't try to fix it like you did with addition. You're going to just add those exponents. So 4 plus 3 is 7. Your answer ends up being 6 times 10 to the 7th. And when you divide, it's pretty much the same thing. You are going to divide your exponents. You're going to divide your coefficients. Here, coefficients. 15 divided by 3 is 5. And then you take those exponents and you subtract them this time when you're dividing. So we have an exponent of 6 and an exponent of 2. Subtract 2 from 6, you end up with 4. So your answer is going to be 5 times 10 to the 4th. Okay. I think this is our last thing, we need to go over dimensional analysis, and that's in your math class. You probably called it factor label method. It uses conversion factors, which are ratios. For example, 1 meter is equal to 100 centimeters, 12 inches in a foot, things like that. So it's a tool that we use for solving conversion problems in which we need to change one measurement unit to another. So this is an example. You are given 4.5 inches and you need centimeters. So if the teacher didn't already tell you how many centimeters are in an inch, you'd have to look that up. But there are 2.54 centimeters in 1 inch. And you see how we put the inch on the bottom here. This basically could be 4.5 over 1, but that's how you can cancel out the inches because we're trying to get rid of that, and we're trying just to keep the centimeters. So then you go 4.5 times 2.54 gives you 11.4 centimeters. Some example, here's another example, and there's going to be a video, or there is a video on some more dimensional analysis examples if you need practice. This one says how many centimeters are in a yardstick, and it's given that 1 inch is equal to 2.54 centimeters. Kind of the same thing we just did. So you're given a yard and you want to find out how many centimeters. So this one's a little more involved because we got to cancel out yards. So how do we do that? So there's how many feet in a yard. There's 3 feet in the yard. So now we get rid of that yard. That's gone. But now we got to get rid of feet because we're trying to get it down to a smaller unit of inches. How many inches in a foot? 12 inches in a foot. So that now cancels out your feet. And then we already said that there is 2.54 centimeters in 1 inch. So, but that allows us to cancel out the inches. Across the bottom, you just have ones. So, that's not going to cause any issues, but you just have to multiply across the top. 1 times 3 times 12 times 2.54, plug all that into the calculator, and you end up with 91.44 centimeters. Again, dimensional analysis is where you're trying to cancel out those units you don't want and only leave the units that you do want. Okay, so if you still have questions about the factor label method, again, you can go look at my short video on some examples, additional examples on Unit 1. Please let me know if you have any questions or need further help.